Howdy, I'm Colton Graham. I'm a fourth year undergrad student at the University of Michigan, and I've been doing research work on characterizing and optimizing the performance of boron loaded liquid scintillators. In the past, a number of designs that use neutron capture element doped organic scintillators have been demonstrated to be useful for capture gated neutron spectroscopy and combined thermal neutron, fast neutron, and gamma counting measurements. Most of those designs have used lithium doping. However, we are attempting to demonstrate the ability to do much the same with boron doping. However, due to the lower Q value of the boron capture reaction, as well as energy deposition from the de-excitation photon from lithium-7, the traditional pulse-shape discrimination that's used to isolate capture events is not effective here. So we've been demonstrating alternate methods of isolating capture events. This mission work is extremely relevant to the MTV consortium due to the ability of using these detectors for monitoring special nuclear material, using thermal neutron, fast neutron, and gamma signals. Additionally, using this detector, we're able to get all of that information through a single output channel, making its operation especially convenient. You can see pictured here on the bottom left the boron-loaded liquid scintillator. It's Elgin 309B, which was provided to us by Oak Ridge National Lab. And you can see we've just coupled it to a PMT to measure its light output. One of the ways that we've been trying to isolate captures is by looking at coincidence from the lithium de-excitation photon in a lanthanum bromide detector. And you can see the setup for that measurement also shown on the bottom left with the lanthanum bromide detector, the EJ309B, and a californium-252 neutron gamma source. In the top of the results, you can see the PSD histogram without any coincidence, and you can see the capture island is very much so bled into the fast neutron and gamma region, making isolating captures using traditional PSD impossible. However, by enforcing coincidence in the lanthanum bromide detector, we're able to much better isolate the captures, which you can see shown here. Additionally, to demonstrate our ability to perform capture-gated neutron spectroscopy, we performed a measurement where we looked at events which were preceded by proton recoils, and you can see once again we were able to isolate the capture island, as well as able to isolate the band of events which correspond to capture events with some energy deposition in the boron-loaded liquid scintillator by the lithium de-excitation photon. One of the theories for why the pulse shape parameter for capture events is so suppressed is the uh, energy deposition from this photon. So we used this measurement to make a determination of the probability of that gamma to escape with all of its energy, which you can see reported here, alongside that value obtained through J force simulation. And you can see in both cases, the gamma escape probability is in excess of 80%, suggesting that an alternative explanation is needed. As a preliminary result, we've been working on using principal component analysis with the digitized waveforms of tagged events to try to better isolate capture events. You can see pictured here a series of gamma events shown in green, capture events shown in black, and fast neutron events shown in red, which are displayed in principal component space. And you can see using this, we're able to achieve much better isolation, or much better discrimination between the gamma events and the capture events using principal component analysis. For comparison, those same events are shown in pulse shape parameter and light output space, and you can see the discrimination is much, much worse. In the future, we hope to continue working on implementing other methods of discrimination for capture events, including digital zero crossing timing, as well as template fitting, with the eventual goal of including all of this information in our principal component analysis to better isolate capture events. Additionally, we hope to make a characterization of the quenching for these detectors as a function of boron loading. The idea being that we believe the quenching parameters with less boron loading will be favorable to better isolate capture events.